One.
Hi, I'm Matthew Amato. I'm here with Team 4 for the processor cooling final presentation.
I'm Ryan Nickel.
And I'm Kareem Pitts.
Yes, and this is our final team presentation.
So our goals, as you know, we have 4 Intel processors that put off about 250 degrees that we need to keep well below that, so that these very expensive, like $5,000 chips don't completely burn or get destroyed or anything. So how we're doing that is designing a heat sink that or a CPU cooler, that also known as a heat sink. We're designing one that out of both either aluminum and copper. Those are our 2 mediums, and the idea is that with the proper design and the proper fin thickness and the proper dimensions, we'll be able to dissipate the heat to keep the chips from burning up and exceeding, I believe it's 75 degrees Celsius. Yep. And of course, there's constraints that we had to build in, specific size requirements, and we had to do it all and still maintain the integrity of the chip. So our goal is to keep these chips at an operable level of 75 degrees Celsius.
So before we went into our project, it would be, as it is for every project, it's always smart to do some research. So before we start getting into modeling and everything, we found this, our model can only consist of conduction means, which is a little difficult because a lot of cooling units right now use convection. So we had to find some means of finding a way to cool it down with conduction. So we found this article posted by, I believe it was a guy named Schmidt. So what he did was he basically put the heated surface surrounded by 6 plates. And so the point that this one mostly used radiation, it seems, but also had a large form of conduction in the center where the plates were attached in basically like a hexagonal fashion around the heated surface, and there was a cold head on top. So the cold head dissipates some heat as well, which definitely is a big bonus. But the main point was that they used conduction with the hexagonal orientation of the plates surrounding the hot surface, which proved to be a good geometry for cooling such things.
So a little more research we did was about the fin design of our heat sinks. So from this diagram right here, you can see this is a pretty straightforward. It looks like a square, and the fins are relatively thin and tall where they're and there's the cuts across the middle. But ideally, you want to make sure that the heat sink can absorb and dissipate heat as needed, and the dimensions are greatly impacted. Like the thickness of the fin, very specifically, is one of the greater dimensions. That, like, the thickness of the fin, how tall it is, how much heat it'll generally dissipate. And of course, this is made with copper, this diagram right here. So copper has a much higher K factor, which is the heat coefficient of the solid. And that of course also is very valuable when you're trying to keep that temperature at a low. So this design right here is kind of, we kind of mirrored this design as our initial design, a square top with rectangular fins. So that's kind of how this was kind of like a platform that we initially started designing from. So the thermal paste is a tool used to actually attach the heatsink to the motherboard. It's basically like a glue, but it's specifically engineered to transfer heat as closely to like a good conductor, like possibly a gold or copper or aluminum. Of course, there is some efficiency loss because it's, the heat flux from the motherboard to the heat sink. That's a very rough surface. So on a microscopic level, those 2 surfaces butting up against each other are very rough. So what the thermal paste does is try to fill in those gaps and make it as seamless as possible to get the proper and most efficient heat flux from the hot source, which is a motherboard, to the heat sink to dissipate the heat.
Yeah, so when we ran through a lot of, or to do all our simulation, we worked through a medium called SolidWorks. So in order to set an ambient temperature in a heat study in SolidWorks, what you have to do is you have to set, it's actually a convection standard, where you have to select all the entities, as you can see on the image on the right. You have to select the entities that are going to be exposed to this ambient temperature in the air. And you also have to set a convection heat coefficient, or a convection coefficient, which for air can range anywhere, or from just non-moving air, can range anywhere from 10 to 50 watts per meter squared Kelvin. And in our case, we had to set our ambient temperature to 298 Kelvin about, which is about 25 degrees Celsius, which is one of the parameters we were given for our design parameters. So now we can move on to our actual designing in SolidWorks. And one of the first designs that we made is one of circular fins. So the reason that we decided to go with circular fins as opposed to, I guess, the generic rectangle or square fins is the fact to increase surface area. So if you look on the right, that is the first model that we've had. And so actually more fins would have been introduced with smaller diameters, so they could fit more on basically the platform right there that would eventually house the chips. But SolidWorks actually could not mesh that many cylinders because of the amount of faces and amount of small faces essentially that it would have to mesh. So we found a good medium, which was this design on our right. This design, all pieces are made out of aluminum other than the paste that is going to glue the processing chips onto it, which was modeled as silicon because silicon was the most abundant material in our thermal paste. This is simply a SolidWorks drawing of the model that was just previously on the last slide. And this just goes to show that all of our parts are in spec because, well, the bottom dimension is inches and the dimension above is millimeters, and they fall within our previously specified spec. So after we ran this heat simulation, well, you can see on the base that, or on the bottom image, that our our initial convection coefficient we set to 10 watts per meter squared Kelvin, which is the low end of air. And so our results yield that it will be below, or that the highest point on the heat sink, or on the total model actually, is going to be below 72 degrees Celsius, which is within or basically within our requirements because we can't go above 75 degrees Celsius. And so if we look at the right image, actually if you look at both the left and the right image, you see that there are certain concentrations of red, which indicates higher temperature. And that is actually exactly where the chips are placed on the board. So obviously if the heat source, or right underneath the heat source is, or right underneath and right above the heat source is where the highest heat is going to be, which is why towards the center of the center of the model, we see a lot of blue because there's no chip relatively close to it. But when you go to the corners, all the chips are evenly spaced. So obviously right above and below, you're going to see the most heat flux, which leads to the higher temperatures. This is a flow simulation done in SolidWorks. Not too surprising. Unfortunately, the temperature is now in Kelvin, but if we convert that, we get to, or the maximum temperature of the chips. This is a cross-sectional cut on the chips. The highest temperature you're going to get is about 72 degrees Celsius, which matches with our heat simulation that we just showed last slide, which is expected. So luckily, both simulations show that we are within the requirement space or requirements.
The second design we chose to work on was to continue using the rectangular fins. The purpose of this design was to maximize the surface area available, although you cannot get as much area, obviously, as you could get out of a cylinder. Typically, most heat sinks, at least earlier heat sinks, were designed in this fashion. So for the first designs, we tried to use the aluminum for the heatsink itself. That in SolidWorks has a K value of 200 watts per meter Kelvin. And again, we use the silicon thermal paste, which has an exceptionally high 400 watts per meter Kelvin that's built into SolidWorks. For these designs, they both managed to stay underneath the constraint of 75 degrees Celsius. However, you can tell by looking at the photos that the heat isn't evenly distributed in either design. In the first design on the left, the heat's to the outside of the heat sink. The design on the right, the heat stayed more in the middle. On the next slide, the second design that we went with, sort of the third model of it, we were able to balance the transfer of the heat out and basically make it so the heat was being evenly distributed throughout the entire heatsink. Again, we went with aluminum. However, with this design, we switched to Coolab Liquid Pro for the thermal paste, which had a K value of 79 watts per meter Kelvin. Both of these designs also stayed well under the 75 degrees Celsius. If you look at the photo on the right, you can see right through the fin where the heat power is being transferred from the thermal paste from the microprocessor to the base of this design. And photo on the left shows how that heat is pretty well evenly distributed throughout the model.
So once we got these initial designs out of the way, and we're like, oh yes, they're working, very good. We got a curveball thrown at us because customers like to change things halfway through designing something. So we got the new update that we got from our customer is the new design is now only allowed to have convection from the ambient open air coming from one side of the board. So instead of ambient temperature air or the ambient convection happening from all sides, you can only have it originating from one side, which definitely causes a lot of issues. So in order to change the cylinder design or the cylinder fin design, the heatsink actually was able to stay as it was. But the main change that we did was we moved the positioning of the chips because the chips right now were evenly spaced out from one another, but now we made them not evenly spaced from one another, which allowed them to have more surface area get hit by the ambient air, which we will see in the next slide. As you can see on the left was our initial design where the chips were evenly spaced out, as you can see, one essentially assigned to each corner. But you look at the right, we see that the chips now, if we were to come from either this direction or this direction, that we would have it be able to hit either these four sides right here or these four sides right here, as opposed to just hitting either these two front sides or these two back sides. So that just goes to show that we increase the surface area of which the ambient temperature would be hitting the chips directly. So this is a SolidWorks model of, if you look on the left, this is the initial model where we had the ambient air coming in contact with every exposed face. But if you look on the right-hand side, the convection, or we pick this right-hand side of the model to be the side that gets the convection coefficient. As you can see, only these outer cylinders and the side plates are going to be able to get the ambient air conditions. So that kind of leaves the question as, oh, how is this going to react in the center of the model? So this is the results that we get from running the simulation that was on the right-hand side of our previous slide. So as you can see, or this time though, we set the convection factor to 40 watts per meter squared Kelvin, because I think that's a pretty plausible assumption if there's no airflow from other directions, that the airflow from the one direction is at least slightly increased. And we had to set a convection factor of 1 watt per meter squared Kelvin everywhere else in order to set an ambient temperature. So as you can see from this design, where there's concentrations of dark red are again where the chips are, right where the chips are, right on top or right underneath. And so the moving of the chips obviously proved to be successful because, again, the highest temperature that we're going to get anywhere is 66 degrees Celsius, which is within spec, luckily. But there could also be argued for room for improvement based off the fact that the corners are still basically pure blue, meaning that there's probably some minuscule changes that can be made in order to spread out the heat transfer a little bit, or a little bit greater.
For the second design, after adding the constraints, we also switched the thermal paste to thermal grizzly cryonite, which has a K value of 12.5 watts per Kelvin. Taking the previous design, we were able to actually reduce the height about 40 millimeters to a total height of 80 millimeters. The maximum temperature for this design we had was 57 degrees Celsius. And that includes the new constraints with 3 sides of having a 1 heat convection as opposed to the 40 watts for all the other surfaces. The heat source is still the same 250 watt heat source. And on the next slide, on the left lower corner of the slide, there's the heat flux plot. And there is a slight ambiguity in this design that the heat flux in this very singular area in the middle of the design has a fairly high value of 200,000. We were trying to work out this whatever's going on there. But if you look at the vector plot to the right, you can see that the heat flux is the strongest in the center of the model, which is why the design was built that way, to help maximize the area there so that the heat can be better distributed throughout the center of the model and ends up with that nice even distribution that we had in the previous slide.
So in conclusion, we can say that all of our these 2 main designs that we have both worked as to how the customer wanted. But now the question is, does our customer have a preference perhaps? Because I think it's always good to go to your customers saying, oh, we have options, as opposed to like one and done, because maybe they prefer one over the other. So, but then the question comes into cost. So if you look at our cylinder design, we're looking at about $2 per foot long of aluminum rods, which would be the rods that extrude from the basically heat source plate. So based off how many issues you run into producing that, it can range anywhere from probably $40 to $100 on aluminum rod material. For thermal paste, we're going to see that the same for both of them, because we're going to be using the same thermal paste regardless. About 15 bucks a piece for thermal paste to connect the chips to the boards. And these chips are actually extremely expensive and are at $13,000 per chip. This is given to us in our design requirements. And now if we want to actually look into the rectangular fin design, which also worked, we're looking at about $18 per 2-inch by 24-inch sheet of aluminum. A little bit more expensive, but you'll get more leftover aluminum from it. They maybe be able to use for other purposes. But the issue that comes there's a factor that is unknown to us right now, because our company has never had to produce such a thing so far. And that's how we're going to manufacture this. So there's 2 means of manufacturing that we can run this through. We either go through subtractive manufacturing from our raw materials, which will get them in the spec and make them smooth, because obviously when you get them in, they're going to be in pretty rough shape, or you assume they're going to be in pretty rough shape. So you got to basically smooth them out, polish them out, make them all nice, because this is a very expensive unit. Don't want to ruin it. And then you're going to have to, once you get all the parts, out of your raw materials, you're going to need to assemble those parts into a configuration that's useful, aka, the fin or the fin designs. So that process, it's going to be a lot more lengthy, and there's probably going to be a lot more issues that can come about it. But then we can also look into purchasing a 3D printer that can print using metals. If we purchase a 3D printer that can do metals, that's excess of probably $500,000. But it's best if we're going to have to repeat this process over and over again. And it also gives the option to use different materials, and basically we can use test prints at some points if we wanted to. So if we're going to repeat this process several times, probably the best idea to lean towards this printer, because we are using SolidWorks at the moment. and pretty easy transition from SolidWorks to a 3D printer. That's kind of one of its main functions.
All right, so here are the numbers. We did a lot of calculations, and we made several assumptions and some modifications. But of course, it's steady state, uniform temperature across the fin thickness. Our K constant for our material is constant throughout. The environment, the H constant for the environment is constant, and the environment temperature is 25 degrees Celsius. So those are all constant, and that the width is far greater than the thickness of our fins. So when going with aluminum as our material to manufacture, it has a much lower K value than copper, which is the 237 versus 401, aluminum to copper respectively. Going with aluminum, we have to make our fin 0.15 millimeters thinner for the numbers to work. So for these numbers to work, we used a slightly thinner fin with aluminum as our material. If we decide to go with copper, we can leave all of our dimensions exactly the same and change our material to copper. And because the K constant is much higher, everything works out. But the main numbers are the total heat transfer of the fin. If you look at bullets 5, heat transfer of the fin, we have for each fin, it's 0.0591 watts per fin. There's 18 fins, and this is on our initial design with the uniform cross section, and so the entire value, heat transfer value for the entire heat sink is 1.0 watts. And then our efficiency using the corrected length, LC, is 0.992.
These are a list of the references, mostly for the figures that we have in our presentation. And this has been Team 4 Processor Cooling, and this has been our final presentation with myself, Ryan Nickel, Matthew Amato, and Kareem Pitts. Thank you.